This is a video in which you will find out more about the action of transition metals and their compounds as catalysts. So here are the learning outcomes for this video. You'll revise some of the key terms: catalyst, homogeneous and heterogeneous, two different types of catalyst. You'll revise also the general way in which catalysts operate, which will be familiar from AS. And then you'll learn specifically how to explain the catalytic action of transition metals and their compounds as heterogeneous catalysts using ideas about electrons. And you'll do the same for transition metal compounds as homogeneous catalysts using ideas about variable oxidation states. So, first of all, definitions of catalysts and different types of catalysts. So, just pause the video for a moment and just check that you can define precisely what the term catalyst means. And then make sure that you can also explain the difference between a homogeneous catalyst and a heterogeneous catalyst. So pause the video to make sure that you can explain and define those two terms as well. Okay, so here's what you should have come up with. The definition of a catalyst is something that can speed up the rate of a chemical reaction without undergoing a permanent chemical change. That's the easiest way of defining it. Now, quite often, you're asked to both define and explain how catalysts work, and if you're asked to explain how a catalyst works, you'll want to add extra information. And here's the key information that you'll need. Catalysts work by providing an alternative pathway that has a lower activation energy. However, if you're simply asked for a definition of a catalyst, then really it's the information in the first line that is important to you. So what then is a homogeneous catalyst? Well, it's simply one that's in the same physical state as the reactants. So, for example, if all the reactants are in aqueous solution, then a homogeneous catalyst would also be in aqueous solution. Another common example is where you've got reactions happening between gases. So if the catalyst is also a gas, then it would be known as a homogeneous catalyst. And you'd have come across examples of that at AS when you've been looking at the depletion of ozone by chlorine atoms in the atmosphere. All of those things are gaseous. So a heterogeneous catalyst, fairly obviously therefore, will be one that's in a different physical state to the reactants. So most commonly that'll be a solid catalyst, whereas the reactants are liquids or aqueous solutions. Notice that sometimes in textbooks you will come across the term different phase to the reactants. Phase is simply a word used pretty much to mean the same as physical state, but it's a slightly more precisely defined term. But as far as you're concerned, for the purposes of exam questions that you'll encounter, we can use the word physical state. Just one word of warning, which is that obviously many of you will be aware of the operation of enzymes as biological catalysts, and many of you may be wondering whether enzymes are classified as homogeneous or heterogeneous. Well, it's probably best to think of enzymes in terms of a completely different type of catalyst. They actually share some features of both homogeneous and heterogeneous catalysts, but I wouldn't try to classify them therefore in one of those categories. I would regard them as a completely separate case of a catalyst, and certainly in terms of the mechanism, that's certainly true. Okay, so you'll hopefully be familiar with this kind of diagram from AS. It shows the idea that you've got a reaction here between some reactants producing products. It's an exothermic reaction because, as you can see, the enthalpy of the reactants decreases during the reaction. However, despite being exothermic, you still require a certain input of energy in order to start to weaken and break the bonds, reaching what's often known as a transition state up here before bonds start to form, releasing energy and eventually causing products to form. So the activation energy is simply the minimum amount of energy that's required to get over that hump to the transition state. It's actually provided by collisions between the reacting particles. So it's technically the minimum combined kinetic energy of the reacting particles necessary for a successful reaction. Now, as you'll see in this example, the activation energy here is relatively high compared to the enthalpy change of the reaction, but by using a catalyst you can reduce the activation energy considerably. As you'll notice, there are two humps drawn in this pathway, and that indicates something that's usually true of catalysts, which is that there's at least two separate steps in the catalytic mechanism, and as you can see, each of those steps has its own activation energy. However, the total amount of energy required to get over that transition state hump is much less in the catalyzed reaction than in the uncatalyzed reaction. That's the key point, as we know about catalysts. This kind of diagram is quite a common question in AS papers, but could certainly come up in A2 papers as well, particularly the synoptic paper, which is one of the papers you will take in June of next year. Okay, so you're required to know something about the way in which transition metals are able to act both as heterogeneous and homogeneous catalysts. Let's deal with heterogeneous first. Now, you have, of course, encountered heterogeneous catalysis in AS, particularly when you've been talking about things like, say, cracking and reforming in the developing fuels unit. And let's have a look, therefore, at how the transition metal is involved, therefore, in that process of heterogeneous catalysis. So the first thing to remember about it is that the first stage of catalysis is the ability of the reacting molecules to attach themselves to the catalyst surface. And that is known as adsorption. And obviously you need to be particularly careful about the spelling of that, because it means something different to absorption. This is a bond forming simply on the surface. Now, the crucial thing that's new for this A2 unit is to understand how that adsorption takes place. It takes place because the 3d and 4s electrons in the transition metal are able to form weak bonds to molecules, such as in this case hydrogen, and those weak bonds are enough to hold the hydrogen attached to the surface. So it's the involvement of the 3d and 4s electrons. Remember, they have very similar energies, so they may all be involved in the formation of these bonds that enables reactions to occur. Now, those can be covalent bonds. If they are, they're relatively weak covalent bonds, although you may come across other examples where the bonds are so weak that they actually are classified as intermolecular forces rather than covalent bonds. As far as we're concerned, though, we are expected to realise that the presence of the d and the s electrons could enable covalent bonds to form between a metal surface and these reacting molecules. Now, if that bond forms, it provides the energy to break the covalent bonds in the reacting molecules. You can see here that the hydrogen gas splits up into individual hydrogen atoms. So bonds weaken and break in the adsorbed molecules. Now, once those bonds have weakened and broken, you can imagine other molecules that are absorbed on the surface may be able to bond to those separate atoms now. In this particular case, this is a molecule of ethene, labelled as ethylene here, the old name for ethene, which has also become adsorbed onto the surface, and it combines with those two adsorbed hydrogen atoms to now become not C2H4 ethene, but C2H6 ethane. So the next step is that new bonds form, creating new product molecules. And finally, of course, those product molecules have to be able to detach from the surface, break the covalent bonds, and diffuse away. If that didn't happen, then there would not be any metal surface available for new molecules to form, and the catalytic process would stop. So all of those stages are vitally important in the mechanism of heterogeneous catalysis. It is possible that you may need to be able to describe the whole sequence of processes there, but the main thing to focus on probably are these first two, the fact that molecules have to be adsorbed onto the surface, and that adsorption happens because of the role of those 3d and 4s electrons. So we can see how that affects the activation energy for the reaction. Here's the activation energy for the uncatalyzed reaction, and here's the processes of, first of all, adsorption, and then the reaction of the adsorbed atoms to form a new product on the surface. And as you can see, it's a very, very small activation energy for adsorption and a relatively small activation energy for the reaction on the surface. overall, the total amount of energy required to be provided in collision is extremely small. It'll be the energy required to reach that transition state there. And so you can imagine that the rate of reaction using catalysis is going to be far, far greater than for the uncatalyzed reaction. Okay, let's deal now with homogeneous catalysis, and this, generally speaking, involves transition metal ions, and as we know, many transition metals can actually form several different ions with different oxidation states. The way that works in the case of catalysis is that you've got a multi-step mechanism in which during one step an ion might be oxidized, and during a second step it might be reduced. Let's see how that could actually lead to a faster reaction. So here's a classic example, and it's one that many of you will be familiar with because it's something that is in a lot of textbooks about rates of reaction, and will feature in therefore many of your investigation research sections. It's the reaction between iodide ions and peroxidized sulfate ions. So here we can see those two ions reacting together. Now it turns out that that's actually quite a slow reaction. Makes sense because of course both those ions are negatively charged. It turns out though that reaction can be catalyzed by Fe2+ ions. How would that work? Well, it would happen by a two-stage mechanism. In the first of those reactions, Fe2+ ions are oxidized to Fe3+ ions. In the process, this peroxidized sulfate ion here is reduced to sulfate ions. If you're not sure about the idea of reduction and oxidation, you might like to pause the video now and just check that you can work out the oxidation numbers of the sulfur atoms in the peroxidized sulfate and the sulfate ion here, and check that you can see that they are indeed reduced. So the peroxidized sulfate is reduced to sulfate in that first step, and then in the second step, the Fe3+ produced at the end of the first step as an intermediate now acts as an oxidizing agent to oxidize the other substance in the reaction, in this case the iodide ions. So we get this reaction occurring here. So the iodide ions get oxidized to iodine, and the Fe3+ is reduced back to Fe2+. So at the end of the whole process, the Fe2+ is left chemically unchanged. Fe3+ is present simply as an intermediate at the end of that first step. It's possible to use electropotentials to actually show that both those reactions are feasible. You may get the chance to do that in class. So you simply need to remember, in terms of the mechanism of homogeneous catalysis, that it's generally a two-step reaction in which an ion is first oxidized and then reduced. That's the end of that short introduction to transition metals as catalysts.